Hello everyone and welcome to this video about the ecosystem model LPJ-GUESS and how to run it on Windows machines. And today I will show you how to use the educational version that is really simple to install and apply, and I will explain how an ecosystem will work briefly. I will not go into detail to the processes, but we will take a look about the output and the variables that we get out, and I will briefly also explain what you could change and what you can try to investigate already with this educational version. So what we have to do is we go to this website here, web.natico.lu.se/lpjguess, and here you will see this one over here. And here in the text you can see an educational version of LPJ-GUESS is available here. So you click this link, which will open here, and there you can download LPJ-GUESS 3.0 for Windows. I already did this, and you will end up with this file over here. It's a pretty old installer. You can see this version is from 2014, but in contrast to many modern architectures and models or software developments, these ecosystem models, they do not change in their core features so often. So although this is back from 2014, the processes are still very similar to what we have in the current versions. So as you can see, I'm not clicking right through this because I already installed this. So instead I will just start. I highly recommend creating a folder called LPJ-GUESS where you will save your in and output, and once you did this we can start already. So you can also see that this icon over here is not very nice. It seems to be missing some link over here, but once it installs we can just start it, and this is how it looks. So it needs a couple of seconds to start, and it will first ask you to set up a workspace folder where input files and output files are going to be written. So because we don't have one, let's say we create a new one, and here I just already said it's good to have a folder beforehand, so here I just use the one that I recently created, LPJ-GUESS. Click on OK, and it wants to create a subfolder here. I just say no because I'm fine with this. Okay, now it says default instruction files are copied, and we can maybe just take a look what's happened in here. So if I open this folder, you can see that I have 3 different files. This ini file, I think it is invisible standardly, but it's not too important, but the other 2 files are important. In other videos I'm not going into too much detail here, but generally this model can be run using 2 different modes, population and cohort mode. And the population mode is it's very simple, where the model will only simulate one tree that represents the whole population of a tree in a given grid cell, and there is no competition for light and no complex vegetation dynamics, and this is kind of rather outdated. Today many scientists, let's say, I don't know, probably all of them that use LPJ-GUESS use the more complex but also more accurate cohort mode, which does not simulate single trees but cohorts of trees. And a cohort, for example, if you go into some spruce forest, let's say, or in the forest, many forests of your areas nearby in Europe is a good example. There you will just find many trees of the same size and age because they were planted as a cohort, and the model assumes that you can simulate all these kind of trees that are having the same height diameter and same crown area and age as one cohort, which is of course much better in terms of computation, because if you can say, let's say, simulate 50 trees by only simulating one, you will have a much better run time. This does not mean that this is the only tree or the only cohort. You can have similar cohorts, multiple cohorts, let's say, of trees with different ages. So this is also something you might have observed already when walking through a forest. There are plenty of trees that have been planted at the same time, especially in the managed forest, of course, which have the same age, and there are also other cohorts that are much younger, and also other trees, for example, beech trees next to spruce trees that are also can be simulated as cohorts. So I highly recommend using this setting. And if you want to go into more detail, I will put 2 papers in the description of this video, which you can check out if you really want to understand what the differences are between cohort and population mode. Very important is that the cohort mode, there the different cohorts can also compete for light, for example, and nitrogen. So whatever tree is dominant in an area is dependent on if the tree has domination on the crown area or not. For example, if it's faster growing, it will have its crown area is quicker to establish, and it will get more light than the others, thereby outcompeting other cohorts, but also other species. Let's take a look what's written in here. The cool thing is that you can just change it easily. You can just use some text editor. I recommend using Notepad++, but the standard editor should also do the trick. Unfortunately, you don't have any syntax highlighting, so you can see it's really just a plain text document without no colors and everything. What you can see here is that text after an exclamation mark is a comment, and here can usually see that the comments describe what the next line is. So here we can see fluxes regarding biomass. Well, biomass are not really fluxes, but the carbon biomasses of the vegetation is going to be written in the file CMAS out, for example. And you can find all these output files at the beginning. Then you have other output files regarding soil evaporation and whatsoever. And here are the general settings of the model. For example, the patch area, how large an area is where the trees can compete. So when you have cohorts, they grow on an area, and this area is fixed, and it's set to 1000 square meter. I would not recommend to change this. This is a very important setting. The number of replicate patches, I am not going to go into much detail here, but of course, when you do grow trees and plants or species and they compete, you need a lot of variability to get stable results. So the randomness plays an important role, and this is how often the simulation is kind of repeated, and at the end the average is taken out of all the simulations. So this value of course does smooth, as it's already said here, the results, but it's also increasing the runtime. So if you set this to a factor 10 for 1000, for example, which is very high, then the model will take 10 times longer. And if you, for example, set it to 10 and patches 10, it's going to be much quicker. Apart from this, you have a brief explanation here for every kind of setting here. For example, water uptake you could change to some other model types. For example, a species-specific water type, we have a parameter, how the plants take up water. A smart water uptake is basically that the plants take the water from the soil where there is the most water, or something like this. You can set on or off the growth limitation for nitrogen, and you have some specific nitrogen parameters. Yeah. Furthermore, this is not too important. You don't need this. The settings over here. And now, as already said, this model, it does not simulate plant species by design, because there's many more species that the model typically can handle. And for many species, we don't know all the parameters. So back when those ecosystem models were developed, there was one concept called plant functional types that are kind of representing agglomeration of species. And here are some parameters that are common to all PFTs. For example, lambda max is the stomatal opening, and I think I will make another video where I explain you in more or greater detail how all these variables are going to look like. And we have this for grass, we have this for broadleaf and needle-leaf trees, or evergreen, summergreen, and so on. And here you can finally see the actual PFTs that the model is simulating. Because it is running as the global version, this means that those PFTs are the most representing the most of the species. So those are most generous. For example, here this one is called BNE, and it's the boreal needle-leafed evergreen tree. So it is supposed to represent all boreal needle-leafed evergreen trees on the world. And next to that one, we have one that has almost the same name, but with an I. So this is a needle-leafed evergreen tree, which is also shade intolerant and has slightly different species, because when developing those models and parameterizing it, people realized that there's a big difference, and you have to separate needle-leaf evergreen into shade tolerant and shade intolerant trees. And here we can really scroll through to other PFTs, summer green tree, we have the temperate needle-leaf tree, and so on. And later on you will find all these PFTs here in your output, and I highly recommend, if you simulate if you're interested in a particular site and you simulate it, I recommend that you take a look here and check out what exactly this tree is and what it represent to do. Yeah, we can continue. Here are tropical trees. We often have this differentiation between shade intolerant and shade tolerant, and we have a rain green tree, and so on. And finally we have grasses. These PFTs nowadays, because we have much more computational power, can also be represented with real species. So for example, if you apply the model only to Europe, this would not be the parameterization or the ins files that you will use, but you would really use the species, for example, beech, Fagus sylvatica, and spruce. Yeah, I don't know if I mixed that up, but you would really use the right species over here. Anyway, so now we're done with this. You can of course change parameters here if you want, but for first start I highly recommend leave everything as is. So we just go back to the model here, and now we can actually go for model run. It's a really simple shell here, interactive window software, I don't know. So we can just go for run, and we, as I said, we select the cohort instruction file, and it says yes, we want to choose that one. But now we need something else, and this is an environmental driver. And here it's interesting because you can use some real climate data here. But I also recommend, it's likely that when you first set up this model, you don't have some climate variables over here, some precipitation data that are made that this model can actually use it from scratch. So I just also recommend that you go for run get clim. And this is a nice small tool, which you can see here, where you can actually pick a place on Earth, which you would like to simulate. So because my special focus in the past couple of years with this model has been the Amazon rainforest, I will select just one point over here. And now you have some settings here. You have a static phase, which is also called model spin up, and you have a transient phase. which is basically the real climate that you are going to simulate. The problem is with the model, you can imagine that on the first day of existence, it does not know actually what plants are going to be there. And I mean, if your climate, for example, usually you don't have any climate data that goes far beyond the 1900. So, but the trees there are much older than this. So how are we going to simulate this if we only have 100 years of climate? And for that one, those modelers came up with a nice solution that they are going to recycle your climate data. So for example, if you have a climate data available from 1950 to 2020, let's say, then the model is simulating and detrending this data, particular temperature, precipitation, and solar radiation, and then it's going to extend your simulation periods by 1000 years with this kind of made up weather and not weather but climate, and that one is then being used to drive the model. And this is also something we're going to see. So here I would just also recommend to leave it for 1000 years, which is something many people do. And I also would say this transient phase is also nice with 100 years. If I do, let's say, simulations with the model and I use real climate data, typically we have between 50 and or 30 and 70 years, but that is fine. So and now we can do some anomalies here, which is really nice. We can click here for enter anomalies. For now, I will leave everything as is, but I will show you another run where I can change this. So what can we do here? We can increase the CO2. And this is only increasing the CO2 in the transient phase as far as I know, but we can see. But we can also increase the temperature and precipitation or decrease it. Let's leave it like this for now, and we can later see what kind of an effect this has. But it's really nice because you can do your own small climate study using one of the state-of-the-art ecosystem models. Okay, so let's leave it like this. And now we can also generate a climate file. And I press here, generate climate file. Okay, here we go. It also, right now, it gives me already the option to explore this file, but I just click finish. And now I have this climate text file here in my folder as well, next to the other 3 files I had. We can also take a look at this one and yeah, open it again with an editor, and maybe I can leave it like this. But here you can see for what's really nice is you can see the year, which is 1, 2, and so on. You can see the CO2 in parts per million, which is set, of course, during the spin up. So the first 1000 years, this is set to pre-industrial levels of 280 ppm. We have precipitation values average per month. This is which this generator created, and we have sunshine. So sunshine days per year. Is it supposed to be sunshine? Yeah. No. I'm got confused. We have, of course, temperature here. So these lines here are the temperature, average monthly temperature. We have the total precipitation per month here, is what you can see over here, and we have the sunshine hours, the sunshine days per month at the end. All right, so you can of course also change this over here. So if you want to include some really strong extreme event, for example, but I don't know, let's go down. This is phase 1, so this is during the spin up, but usually we are more interested into phase 1, the simulation. So the last 100 years. So if you want to say, I want to include some really extreme event here, you could, for example, reduce the precipitation of this year drastically and give it, for example, only 10 millimeters per month, which for a tropical rainforest is very intense. But this is only optional, and yeah. Unless you know what you're doing, I recommend not to do so. Anyway, so finally, now we can run the model. So we click on run, everything is set up, we have a climate, we have an instruction file, so the model should do its job. And here we go. So what do we see here? So basically now we get this little window here, and it says we have no anomalies, and it says we have 1000 years spin up, initiation also called here, and we have 1 year of the scenario phase. And it tells you every 20 seconds about the progress. So here it's about taking 3.5 minutes more time. We have already 8% ready. And here we have plenty of small output videos. Yeah, and while this builds up, you can see it's simulating in the background. You can also see this by this very nice animation here on top. We can take a look about some of the files, and I will explain them to you. Okay, starting, let's say, with the first, or let's say one of the important one. Here we can see carbon biomass versus time over time. So basically here the whole simulation started with nothing, and now you can see some colors are emerging over here on some lines, and you can see what kind of PFTs they are. The y-axis is carbon biomass in kilogram carbon per square meter. So we can see already 400 years have been simulated, and regarding biomass, there's only one PFT dominating, and which is not, let's say, which is not surprising. It's the tropical broad-leaved evergreen tree. So it's the main tree that is supposed to represent the tropics. And it's interesting because we can see during the spin-up phase already quite some interesting dynamics going on. It's not so easy to tell, and usually it's not so clear what is going to happen. So what's happened with the vegetation during the spin-up is should be really interpreted carefully. What we can see here after 100 years is that we have a disturbance interval where everything is killed because some properties of the soil have emerged. So you can imagine if you have a tree that is dying because it's getting older, then you have litter fall, and then you have soil decomposition, and in the beginning of the model everything is very random, and this is going to help the model set up some soil property. So after 100 years, the vegetation that goes has a more realistic soil property, so the soil is better set up after that time. And I believe here, because the model has some so-called background mortality, so when the trees grow older and older, they are having a likelihood to die, and especially at very high ages of 400 years or something, this mortality kicks in and kind of reduces the biomass and kills the trees. And you can already see that now we're about at 800 years. It's kind of leveling out with a biomass of 12, 14, 15 kilograms carbon. What else do we have? We have night primary productivity, which is basically the productivity of the plants. So basically how much carbon is invested, have the plants available at the end of the year that are going to be invested into the different compartments of the plant. So for example, if a plant has typically here around 0.75 kilograms carbon available, it is has an allocation scheme, and it's putting, let's say, typically 30% into leaves, 30% into roots, and the rest 40% into the sapwood, for example. This is very dynamic, so it's not fixed fractions, but it depends really on the simulation and everything, and on the tree species and on the biomass. So it's a very dynamic process, and I will also put a paper if you are interested in how plants are distributing carbon into the different compartments. I will make another video about this, and yeah, you can take a look. Okay, so model run terminated. We can close this. It just tells that it's done. Or maybe we can take a look at the end what we have after. And can we scroll down here? After 1,000 years, it says we have a carbon biomass of basically, I don't know. There should be something down here which I cannot reach at the moment. Maybe I should enlarge this. Yeah, there we go. So maybe we can just take a look at these lines first. Here you can see we have a total carbon of 12.119 kilograms per square meter, and it is basically this tropical broad-leaved evergreen tree that is being present here, which is of course unexpected. We have a little bit of this intolerant tree over here, and we have a little bit of grasses and the rain green trees, but they are really negligible in terms of carbon biomass per square meter. So let's keep this 12 kilograms in mind. We have an average, we have an MPP at the 2001 of 0.86, which is kind of a little bit too low, I would say, for this area, but let's keep it like this. And we have an LAI. This is a so-called leaf area index. Basically, if you take an area of a plant, of the canopy, and you take one leaf and you look through this leaf, and basically how many leaves do you have per square meter. So for example, leaves overlap in average 5 times per so you have a 5-time overlap of leaves, and typically the higher this value is, the more photosynthesis and growth and MPP plants can have. Okay, finally, we don't have to go through all of them. There is this LAI development over time, which is kind of 5 is a good typical value for a tropical tree, so everything makes kind of sense over here. 8 structure I think is not really interesting and not really working, so let's close this. What else do we have? We have water fluxes. Also quite interesting here for the tropics. Very interesting is the transpiration, and you can see that there is nothing really happening during the phase. It's kind of constant at 400 millimeters, which is quite a bit too low, I would say. It's supposed to be higher in this area, but yeah, it doesn't really change over time and keeps constant. What's also interesting here is that we cannot see an increase of this. Can we? Let's take a look at another graph. No, we cannot see an increase in carbon biomass here over time during the scenario time, and that's quite interesting because we have more CO2, and typically if you have more CO2, photosynthesis will give you a little higher gross primary productivity, and of course in the first place you think more photosynthesis, more CO2 will lead to higher NPP, productivity will lead to higher growth rates, and should also lead to higher biomasses. But it's not that simple, let me tell you at least this. Of course, you cannot just bring it down to this if you want to explain an overall effect. So when you want to really investigate the fate of the Amazon rainforest, for example, you need to consider all other things as well. For example, the more frequent occurring drought events that of course are killing trees. So the benefit of having more CO2 is of course versus the big downside of having more droughts during drought events and during during climate change. Okay, but anyway, you can find an explanation of this also in the help settings. So let's maybe put this back here, and I would say focus only on this productivity and the carbon biomass for now. So what I'm going to do now is we are going to change a little bit of the settings so that you can get an idea what else is possible. This is some other settings. You can also show some 3D vegetations, but yeah, you don't actually need this. I would say this is not important. You can just say some of the settings. So we can go here on run again. And for now, let's keep in mind that we have, after our simulation, we have 12.119 kilograms of carbon and 0.8, let's say, NPP. So now what I'm going to do, I'm going to show you something interesting. Let's go for this get clim again. We just take the same position here, and now we do some anomalies. And just to give you an idea, let's say we increase the CO2 by a dramatic 300 ppm, and let's see what the model is going to do. And say OK, and we can again generate file, and I just overwrite the settings. It would also make sense to save it if you really want to explore it. Now I clicked on explore here. It actually did not overwrite it, so now we have climate 0. Yeah, we can take a look here, and now we can really see that our CO2 levels here, which is this line, are really going high up to 580 ppm within 100 years, which is a very high value. Anyway, so let's see what effect this is going to have to our simulation. So let's go back into the model here and hit run again. And you can see it should not take much longer. It should be basically the same site. And I'm not expecting to see something different during the spin up, because the CO2 increase is only applied to the scenario phase. So in our case, to the last 100 years. So let's see what's going to happen. We can see again here, after 100 years, we have this patch, so-called patch destroying disturbance. Everything that is in our grid cell or in our simulated area is going to get killed, so that we can have some better soil properties once the model is emerging. And you can see that it's not such a big difference here. So the graph looks quite of the same from 0 again. We have first this brown one a little bit dominating, but it's really quickly outcompeted by this TRBE, this kind of green line or aquamarine color that is kind of emerging quite fast. So I'm really expecting to see a very similar output of the model for the first phase, so this 1000 years. And you can again see here that it's simulating, and we have this grid cell selected. This was the point that I showed you in South America. We can of course select different points. Yeah, and you can see again that this drops after a couple of 100 years. So our plant, our PFT here, that is really dominating and really having a high biomass here of 30 kilograms per square meter, which is enormous, is going to be leveled out again. Yeah, I think we can also close this. LAI I explained. You can see there's not much going on. That's interesting. So if you close it, it comes up again during the simulation. So better not to close it. Yeah, so we have to wait a bit. In the meantime, precipitation, for example, is also something that you could reduce. So we can just see here that the temperature in this case is, we left the temperature as is. Maybe we should have also added a temperature anomaly, but I'm a fan of keeping first of all, to understand what the model does, I prefer only changing one thing at a time, because if you would change everything, you do not actually know what's going on and what is really the driving force for the change that you might observe. So, but as you've seen in the window where I set it up, you could also add other anomalies, the temperature anomalies, a precipitation anomaly, or some nitrogen anomaly, which I'm not going to get into detail here. So now we are at almost 800 years and the model keeps going. And yeah, it's 1:30 left. So I highly recommend for you to check this model out, to download it, to play around with it. And basically this is the version 3.0. We now have 4.1, but there hasn't been too much change to all the processes and vegetation dynamics. And it's the real thing. It's not like a version that can do much less. It's the whole model and how it works. So basically, if this model is also used for climate protection runs, for not climate protection runs, but for future runs, and it also kind of contributes to the IPCC. So you really have something that is used in the current stage of research. So as we can see, we have the scenario phase, the initial phase. We have it is done. We ended up with a similar value before our scenario of 14.0.2 kilogram, NPP 0.88. But now you can already see here in this picture and this picture something different happened. We have a ginormous increase in NPP, and we also have a straight increase in carbon biomass, of course, because if there's more NPP and the plants can invest in more compartment, we have also very likelihood that the biomass is going up. Same applies to LAI. So plants are also, if the plants investing their NPP into leaves, we have of course more LAI also. And you can see here at the end, the biomass from 12 point something is dramatically increased to 21.85, and the NPP from 0.86 is also much higher to a 1.3. So the plants basically really, according to the model, really benefit from high levels of CO2. And I already mentioned this before. This does not mean that climate change does nothing, or that that the kind of rainforest will buffer climate change. So the more CO2, it will take up more carbon. It's not that easy. And let me just say this, and to finish this, of course, you need to consider what also is going to happen during climate change. And you have more higher temperature, which you can add here and see what's going to happen. And you can also change the precipitation to include drought events in the future. And this is something altogether, of course, which will change these results over here. But let me tell you one thing. In this current version of LPJ-GUESS, the model does not a great job in representing mortality induced by droughts. So, however you will change these values, and I highly recommend you to do so, at some anomalies, you will see that you will always end up with a positive effect with high CO2. This is something what I did, and I can link you some papers in the description as well to see what I'm currently working on. And I improved basically this drought feedback. So if you have droughts, what will happen to the mortality? And of course, if you have higher mortality, this carbon biomass will decrease. And so far, all of these DGVMs or ecosystem models do a poor job, or let's not say poor, do not the best job when simulating drought-induced tree mortality, and most of them do not have a process associated with drought in their model. And I also link a paper, it's a study from 2013 that I recommend you check out to see that if you apply those ecosystem models to a similar location as we have chosen here in our small experiment, you will see that none of the models are capable of reproducing mortality observed by stronger drought events. And with this, I would like to end, and I hope that you learned something about the model, not really about the whole structure of the model or the processes, but somehow the output, and how, for example, we can make a very small case study with increased CO2 and its effect on the vegetation that is simulated in the model.